Hello, we are group one and we are doing our project on characterization using IR and NMR spectra. My name is Talia and I'm going to be going through part A right here. So part A is determining the molecular formula based on the data that we're given right here. So through some trial and error, we can determine that this one is not going to be our M plus because if we multiply 80 by something to get to 100, it's going to be times 1.25. If we do that to this number right here and then divide by 1.1, we're going to end up with 16. And we know that we cannot have 16 carbons because if we multiply that by 12, it just ends up the molar mass would be too high with the data that we're given. So we know that that one is not our M plus. So then we move up to the next one and we guess that this one is going to be our M plus. So if we multiply this by 7 to get 100 and then we multiply 1.1 by 7 and then divide by 1.1, we end up with 7. So that would tell us that we have 7 carbons in our molecular formula. And then we look over here and we see our mass is 114. That tells us that we either have an even number of nitrogens or 0 nitrogens. Based on the data and our molar mass, so if we have 7 carbons times 12, we get 84, and then our mass, 114, minus 84, that leaves us with 30. So it wouldn't make sense for us to have 2 nitrogens. And we also know based on this data that we don't have any halogens. So if we could just guess based on this that we have an oxygen in there. So if we minus 16 from 30, we end up with 14. And that would make sense for that to be our number of hydrogens.
Okay, hi, my name's Robert, and I'm going to walk us through the index of hydrogen deficiency. So to solve this, we're going to use this formula. All right, and here the X is going to represent the halogens. So we don't have any of those. So we cross that out. Same with nitrogen, we don't have any of those. So now we're left with 1/2 of 14 plus 2 minus 14. So these are going to cancel out, and we're left with half of 2, and that's going to be 1. So this is our index of hydrogen deficiency. That's going to tell us that there's going to be one site where we're hydrogen deficient. So that's either going to come in the form of something like a double bond or a ring. And now for this next part here with the IR spec, let's go blue. This is going to be our range where we're likely to see a double bond appear. So we see that there's this little peak here, and it's very prominent. So it goes pretty far down. If it were a little shorter, it could be something like a carbon-carbon double bond. But since this is at 1713, this is going to tell us that this is most likely an oxygen double bonded to a carbon. So it looks something like this. There's a carbon. Let's go here. There's the rest of the molecule. All right.
Hi, my name is Joe. Now let's move on to some of the NMR data. So NMR in general is one of the best tools that we have available for identifying molecules, specifically the hydrogen NMR, but we can also make some useful conclusions from the carbon NMR as well. So what this tells me right from the start is that we have a lot of symmetry in our molecule. We see 4 peaks, which means 4 unique carbons, but as we previously found, we know that there's 7 total, meaning that there are electronically equivalent carbons in our unknown molecule. Now we can look at the shielding and deshielding. And what first grabs my eye is this one all the way downfield past 200 ppm. And that must be the carbonyl carbon having its electron density pulled away the most because it's right next to that electron withdrawing oxygen. The rest of our peaks appear from the 0 to 70 ppm range, which means they're likely sp3 hybridized carbons. And this one is more deshielded than the other 2, meaning it's likely the closest to the carbonyl carbon. Then the next 2 peaks aren't experiencing as much the effects of deshielding, which means they're farther away from that electron withdrawing oxygen. Now let's build off more of this information using the proton NMR. We know that we're going to see some symmetry. We know that we have equivalent carbons. Let's see what we can learn from the splitting patterns in the proton NMR.
Hi, my name is Jimena, and I'm going to be explaining the HNMR and the final structure of our molecule. So as we previously had said in our IR spectra, we have this double bonded oxygen to the rest of our carbon groups. So here on there, I'm going to apply that with the aspect of our carbon NMR as well. Looking at this, we can look at the multiplicity of the peaks as well as correctly assigning the correct amount of hydrogens to each carbon. And this oxygen double bond acts as the symmetrical point like Joe had explained. So going off this, we know that this one carbon is a symmetry, so there must be 3 carbons to each side of it. So 1, 2, 3 at that end. And here we're going to apply that the hydrogen peaks also verify this. By applying the hydrogen peaks to each carbon, we can see that this first one, the most deshielded one, to the leftmost part of our graph, is going to be the one closest to the oxygen double bond. And it says we have 2 hydrogens on there, so we can put those 2 there. And we can verify this knowing that it's only split by 2 directly neighbor hydrogens, which is our next hydrogen peak. When we look at this hydrogen peak here, we can see it's multiply split with a lot of multiplicity, which would be the hydrogens on both sides of this carbon. And it's only 2 hydrogens there, so we will put 2 hydrogens there. Looking at the last peak, we can verify all of our molecule because it is a methane group at the end here with 3 hydrogens here. And the multiplicity shows that there's only 2 hydrogens next to it because it is a triplet. So our final molecule, knowing that this is a symmetrical point, is going to look like this. And the hydrogens are implied there since it is a skeletal structure. Thank you so much for watching our video project.